Have you ever really stopped to wonder why some things bend and other things just break? I mean, everything around you, from the chair you're sitting in to the phone in your hand, every single object is speaking a kind of secret language. It's a language of properties that dictates exactly how it behaves. Well, today, we're going to learn how to translate that secret code. Okay, let's start with something super simple. A paperclip, right? You unfold it, you bend it into some new shape, and it just stays that way. It doesn't fight back, it just accepts its new reality. But why does it do that?
Now contrast that with the rubber band. You can stretch that thing out, pull it as far as you want, and the second you let go, snap! It's right back to how it started, like nothing ever happened. That's a totally different reaction to the same kind of action.
So what's the deal here? Well, this isn't magic, it's material science. The reason these two objects act so differently comes down to a set of invisible rules. They're fundamental, hidden properties. And today, we're going to decode those rules. We're diving into what are known as the mechanical properties of materials. This is literally the language that engineers use to figure out what to build our world with. It's the hidden code that determines if something is going to bend, break, stretch, or survive a scratch.
First up, let's tackle strength. Now that's a word we throw around all the time, but in the world of engineering, it's got a way more specific, way more interesting meaning than just being tough.
At its core, strength is all about resistance. It's about how much of a beating a material can take before it either breaks completely or gets bent out of shape for good. But here's the kicker. Not all force is created equal.
So strength actually breaks down into a few key types. You've got tensile strength. Think of a rope in a game of tug-of-war. That's its ability to resist being pulled apart. Then there's compressive strength. Picture the massive concrete pillars holding up a bridge, constantly being squashed by weight. And yield strength? That's the point of no return. It's that exact moment our paperclip gives up and decides, you know what? I'm just going to stay this way.
Okay, so pushing a material past its yield strength means it's changed forever. But what if you need the exact opposite? What if you need it to bounce back no matter what? Well, that brings us to the defining feature of our rubber band, elasticity. See, while our paperclip had really low elasticity and just gave up, the rubber band is a superstar in this category. You can stretch it, you can apply all that stress, but the moment you let go, it remembers its original shape and snaps right back. That right there is elasticity. I think this quote just nails it, doesn't it? High elasticity basically means high resilience. It's the material's ability to take a punch, get bent out of shape, and come right back for more, totally unfazed. Bouncing back is great, for sure. But what if you actually want to bend something into a new shape, and you need it to do so without breaking? This is where one of the most important properties for actually making things comes into play: ductility. The absolute classic example here is taking a chunk of metal and pulling it into a super thin wire, like the copper we use in all our electronics. A ductile material doesn't just snap when you pull it. It stretches, it thins out, it deforms. This property is precisely what lets us form a paperclip in the first place. And to really understand ductility, you've got to meet its opposite, brittleness. A ductile material like steel kind of gives you a warning. It'll bend and warp and groan before it fails. But a brittle material, like a ceramic plate, it gives you nothing. It just shatters. No warning, just sudden failure. They're two completely different ways of dealing with stress. All right, our last major property for today is hardness. Now, this has nothing to do with being pulled or squeezed like strength. This is all about surface warfare. It's about resisting scratches, dents, and just general wear and tear. Yeah, I know. Localized plastic deformation sounds incredibly technical. But really, it's just a fancy way of saying a scratch or a dent. Hardness is all about one surface battling another. So when you ask if something is hard, what you're really asking is, how easy is it to scratch this thing? And who is the undisputed champion of hardness? You already know it's the diamond. It scores a perfect 10 on what's called the Mohs scale. That means it can scratch pretty much any other material on the planet without getting a scratch back. And this just gives you a great mental picture of how that scale works. It's like a ladder. Your fingernail can scratch talk, but a copper penny can scratch your fingernail. Steel will scratch the penny, and of course the diamond at the top of the ladder can scratch every single one of them. It's all relative. So there we have it, our 4 key players: strength, elasticity, ductility, and hardness. So how do they all fit together? Well, that's where things get really interesting. That's the art and science of engineering.
This chart lays out the puzzle perfectly. For a skyscraper, you need something with high strength but also high ductility, so you go with steel. For a tire on your car, you need insane elasticity, so rubber's the obvious choice. And for a chef's knife that needs to hold a super sharp edge, you want extreme hardness, so you might pick ceramic. And the reason they're all so different comes down to their atoms. Ceramics have these tightly packed, rigid crystals that make them hard but brittle. Rubber, on the other hand, has these long, tangled molecular chains, kind of like a bowl of spaghetti, that can stretch out and then snap back into place.
And that right there is probably the most important thing to remember from all of this. It's never about finding the one best or strongest material. It's always about understanding these trade-offs and picking the perfect combination of properties to get the job done. So now you get it. You can speak the language of stuff. Just look around the room you're in right now. Why is the wood of your desk hard and strong? Why is your phone's charging cable ductile and flexible? The secret code is literally everywhere, and now you have the key to unlock it.